This is in continuation of our discussion on electrical conduction in ceramic materials. We have earlier discussed about the few basic concepts of electrical conduction, some parameters which are of importance in describing the electrical phenomena in different materials. We have also started discussing about the various theories put forward for the explanation of conduction behavior, particularly in metals to start with. We have already considered the so called ideal gas model for the electrical behavior of metals, and then took up the free electron theory of metals. In that context, we saw the energy diagram with respect to k vector, and it was a parabolic function, and we also defined the Fermi energy, that is the highest energy up to which the energy states are filled up depending on the available free electrons in the particular solid. And although it has been we have drawn a 2-dimensional curve, but actually it is a 3-dimensional figure, and in also we mentioned that these energies are actually discrete energy levels. They are not a continuous energy levels as per the Pauli exclusion principle. So, they are all which is expected in any free electron. So, they are actually quasi continuous curves, and that is the reason some dots have been put there along the line. Next, we talk about what is the temperature effect when you this is what we get at absolute 0, the E versus k curve, E is proportional to k square. If we want to look at the temperature effect of this distribution of the kind of occupancy, we have seen either there is a 100% occupancy or there is 0% occupancy. Okay. So, depending on the available electrons, these are fully occupied, 100% occupancy, and then above that there is a 0% occupancy, there is absolutely no electron available, although the energy states are there. If the electrons can somehow acquire higher energy from external sources, it can go to the higher level. However, there are two ways by which the electrons can basically acquire some additional energy. One is the external electric field. So, that is possible. So, under that condition, some of the electrons will acquire higher energy and go to the higher energy level above the so called Fermi energy. There is other way of acquiring energy, that is of course by temperature. So, if the electrons acquire additional energy from the thermal energy supplied to it, then we have to consider how this distribution changes, and that is given by the so called Fermi-Dirac distribution function P as a function of E. So, with increasing temperature, the electrons just below the Fermi energy get excited to the energy levels higher than the Fermi energy following Fermi-Dirac distribution function. This has been the energy diagram has been plotted here in a different way. So, this is the energy which was there in the vertical axis, here in the horizontal axis, and here it is the probability. It is the probability function of occupancy of a particular energy state. That means, this energy state, what is the occupancy factor? whether it is 0% occupancy, 5% occupancy or 100% occupancy. So, this 1 means it is fully occupied. So, these energy levels up to this is fully occupied, and the distribution function is can be expressed in this manner: P equal to 1 over 1 plus exponential E minus E f by k T. Once again, k is the Boltzmann constant and T the absolute temperature, E the actual energy of consideration, and then E f is this energy, that is the Fermi energy, which we have seen earlier as this energy. Okay. So, this is Fermi energy. We are plotting this curve in this manner. So, this was the vertical axis E here, and there it is the horizontal axis. Okay. There is no k here, k term, the wave vector term is not there, it is k is a Boltzmann constant here, that one has to remember. So, this probability function, if you plot, it looks like this. Okay. So, this is at t equal to 0, at 0 degree Kelvin, that means this is a rectangular curve, rectangular plot, which means up to E f the Fermi energy, the probability factor is 1, which means fully occupied, or full occupancy factor is 1 or 100% occupied. So, that happens at 0 degree Kelvin or absolute 0. So, the curve is like this, the dot arrow as per the dotted line here. So, it is a rectangular or a complete discontinuity at E f from 100% occupancy to 0% occupancy here, and then it continues there. Whereas, if I think there is some mistake here, it is not at 0 degree Kelvin, it is T greater than 0 degree Kelvin. Let me see whether I can make this change here itself. At T greater than 0 degree Kelvin, this is at 0 degree Kelvin. Okay. Whereas, at T greater than 0, this becomes the kind of situation. Okay. It changes more or less in this fashion. We will look into that later, more details. Basically, what it means, very close to the EF, the electrons which are having the energy is very close, just below EF, will acquire some additional energy from thermal energy, they will absorb some thermal energy because of the higher temperature, and they will cross over the Fermi energy and go to the higher level. So, some of the energy, some of the electrons will be emptying this place, will empty this space and go to the additional space here. So, this is higher energy than EF. So, there will be again a distribution, from 0 it will increase to 1 occupancy, but higher is the energy level, lower is the occupancy factor, and closer to the energy level, that means closer to EF, higher will be the occupancy factor. So, it will increase from here, from 0, it is 0 occupancy factor. Beyond this point there will be no occupancy, the energy states will be completely empty, but up to this there will be some finite occupancy, and then that quantity will increase slowly and becomes 1 at a energy little lower than the Fermi energy. So, basically it means that some of the electrons having very energies very close to EF will acquire additional energy and go above EF. So, that original definition is not going to be valid anymore. So, in this condition at temperatures greater than absolute 0, it is not the highest energy level up to which the occupancy is there, it is more than that, but at EF the occupancy is 50%. So, this line crosses this vertical line at 0.5. So, for EF at Fermi energy the occupancy factor will be 50% and rest 50% will be empty, whereas more electrons will go above, some amount of electrons or some fraction of the electron will go above the EF and occupy higher energy levels. That precisely it says the Fermi-Dirac statistics, okay, or Fermi-Dirac distribution function. That is a very important concept where it looks at the temperature effect of the occupancy or the energy levels of the electrons at different temperatures. This is also almost the same curve, but at different temperatures. The same probability function E as a function of E, and one can see at EF there are 3 different temperatures. Temperature is increasing in this direction. So, this is at 0 K or absolute 0, the green one is a step jump or step disconnectivity step change here, okay, from suddenly from 100% it goes to 0% at EF, and that happens at 0 absolute 0, but as we increase the temperature the curve changes and from steeper to it becomes a more flatter curve, okay, more flatter curve. So, but all the curves go through this point P equal to 0.5. So, 50% occupancy. So, that do not change, that is independent of the temperature. So, only at 0 degree Kelvin it is 100% occupancy, otherwise any temperature above 0 degree Kelvin it is always 50% occupancy. So, that value does not change irrespective of the temperature, and that is a very important observation or important aspect of this distribution function, the Fermi-Dirac distribution function. So, it also means that this area under the curve, this area actually is proportional to the volume or the total number of electrons which will acquire higher energy and go to the higher energy level, acquire additional energy and go to the higher energy level. So, this area under the curve, this area bound by this curve actually, and this area bound by this lower portion of the curve, it should be equal. Okay. So, this volume, this area and this area must be equal. Similarly, for other curves also. So, the exactly equal number of or the same number of electrons which leaves the lower energy level goes to the higher energy level. So, the total number is conserved. So, with increasing temperature more and more electrons acquire higher energy level, higher energy from the thermal energy thermal system, and it goes to the higher level above the EF. The Fermi-Dirac distribution function is a symmetric function. At any temperature above absolute 0, the same number of levels below EF is emptied as the number of levels above EF are filled by the electrons. So, that is what I explained, that the area under enclosed by these curves are same on this side as well as on this side, irrespective of the temperature. Whatever may be the temperature, this area and this area must be same. So, which means basically the same number of electrons will be on the both sides. So, whatever sides will be emptied, it will be filled up here. So, that is a very important aspect of Fermi-Dirac statistics or Fermi-Dirac distribution function, which can be applied for the Fermi energy. Well, in addition to normal energy or energy distribution, one can also have another parameter, that is known as the density of states. Now, the density of states is the number of electronic energy states per unit energy, that is the derivative d and dE, which is often written as GE or sometimes NE also. The number of electrons per unit energy. Okay. What is the total number of electrons at any particular level? What is the energy energy states? Okay. So, NE is also depends upon the probability that a given state is occupied, that is Fe, the Fermi-Dirac statistics. Okay. So, it is basically GE multiplied by Fe becomes NE. So, this is your NE, once again this is the energy scale, and this is NE. If you plot this, then this also becomes a parabolic function, and here it will be the EF. Okay. Here will be this will be the EF. So, what we have plotted earlier is basically a probability, and here it is the number of actual number of electrons which will be available at particular energy level. So, this has some amount of similarity with the earlier curve. For example, at t equal to 0, this up to EF everything will be again filled up, and this will be the distribution function. That means, at the lower temperature, at the lower energy, less number of electrons will be there, as higher energy more number of electrons will be there, more number of energy states will be available. Okay. So, that is also we can get from EK curve. So, at this temperature, this energy level, this will be the number of energy states available, whereas on this side this will be the vertical line will be the energy levels available. So, higher is the energy level, more and more number of energy states are available, and at EF it will be the maximum. Once again one can apply the Fermi-Dirac distribution function here, and at temperatures greater than 0, this will be the situation. Some of the electrons closer to the electron, just below the EF or Fermi energy will be excited above the Fermi level, and again the number of states below and above will be equal. So, this is the variation of what we call the energy density of states. At any particular energy level, how many states are available, how many energy states are available. So, at 0 it is only 0, whereas as we increase the energy, more and more number of energy states are available following a parabolic curve. This I have mentioned earlier, as per Fermi-Dirac distribution function, Fermi energy is the energy at which the occupancy factor is always 0 irrespective of the temperature. Okay. So, this is a definition which is useful for higher energy, higher temperatures, at 0 temperature, at absolute temperature is the highest energy level up to which the states are occupied, whereas if it is non-zero, the temperature is non-zero, then this will be a better definition or is actual definition. That means Fe, because at the under that situation Ef or the Fermi energy is not the highest energy level up to which the electrons are available or electrons are occupied, energy states are occupied. So, it is only the 50% occupancy, and that is a constant irrespective of whatever temperature we use. Now, consequence of this free electron theory, these are some of the considerations of the free electron theory. We have a EK curve, and there is a energy called the Fermi energy up to which the electrons are occupied, and temperature above 0 degree Kelvin, some electrons will occupy attain or get excited to a higher level. So, these are the major observations of this theory or outcome of this theory. So, at 0 degree, consequence of what happens at 0 degree Kelvin, Ef at 0 is h bar square 2 me 3 n pi square 2/3. So, where n is the electron density or the energy states, that is the number of electrons per unit volume of the metal, not at density of states, it is the number of electrons per unit volume of the metal. And calculations show that Ef at Ef 0, that means at temperature 0, it is about 5 to 10 eV electron volt. However, thermal energy at room temperature is much less. Okay. It is about kT is about 0.025 eV. So, kT is much less than the Ef or the Fermi energy at 0 degree Kelvin. Only electrons occupying level close to Fermi level Fermi energy will participate in the conduction phenomena, since only these electrons can be excited into the higher energy states by electric field. Okay. So, that is also another important aspect, that only the electrons occupying levels very close to the Fermi level, not because other other electrons will need much larger energy to be excited above the Fermi level. Only the electronic levels or the electrons having energy very close to Fermi level will get excited both by thermal as well as by external electric field. From quantum mechanical consideration, energy supplied by the electric field is sufficient to excite electrons from lower to the higher energy levels close to the Fermi level. Okay. So, although we have also seen in the Fermi-Dirac statistics or Fermi-Dirac distribution function that as a function of temperature or as temperature is increased or more thermal energy is delivered to the system, electrons very close to the Fermi level gets excited. Similar is the case with the applied field. If you apply field to this system in addition to the temperature, once again the same thing will happen. No electrons having this level of energy will get excited here. Only the electrons having very close to the Fermi level, energies close to the Fermi level will cross over and go to the higher level. So, that is another important aspect. It is not only the thermal energy, but with impressed EMF or the electrical energy also have the similar effect. So, that is what is mentioned here. From quantum mechanical consideration, energy supplied by the electric field is sufficient to excite electrons from lower to higher energy levels close to the Fermi level or Fermi energy. So, that is also another aspect of this theory. With this one can find out what will be the temperature dependence. If an electron possesses the kinetic energy equivalent to EF, one can write EF equal to, in fact it introduces a velocity in terms of the kinetic energy the Fermi energy, and that velocity has been termed as Vf, the Fermi velocity. So, half mEv square, once again the kinetic energy, if the kinetic energy is Ef, then and the velocity of that electron is Vf Fermi velocity, then half me v square, or Vf will be equal to 2 Ef by me. So, the energy of the electron having the energy having electron the electron having an energy of Ef will have a velocity of this, provided me is the mass of that electron. So, Vf is the Fermi velocity, in terms of which sigma the conductivity, because there is always a velocity term in the conductivity. So, it becomes E square n Lf m Vf, where Lf is the mean free path again. Okay. Again some kind of a collision has been assumed, but what exactly it means need not be understood, but this term is some kind of a mean free path, because in the way we have defined our conductivity term, it contains some velocity term, it also contains the distance covered by the charge species. So, sigma is expression of that this is the velocity term and this is the distance term. So, E square n Lf m and the mass. So, to continue that, it may be shown that because of this wave particle duality of the electrons, the collision is not between the electron and the stationary ion, but due to the interaction of the electron wave and the lattice vibration or the phonons. Since by this time we are not considering only the particle nature of the electron, we are also considering the wave nature, and that is how the wave vector came and the de Broglie wavelength also came. So, it is basically a wave, and that wave is interacting with the lattice vibration, because the lattice is also vibrating and it has a different modes of vibration, and those are called the phonons. So, the collision here is not with the static ion core, but it is the vibrational mode of the ion core, and that is possible because you have a wave nature of the electron. So, the electron is also a wave, and the lattice vibration is also generating some form of waveforms. So, these two will interact, and that is what we are talking about, the collision. Okay. So, this collision and the earlier collision which we considered in the ideal gas theory is are little different. So, their characteristics also will be different. In case of phonon scattering, the mean free path is inversely proportional to the temperature, and thus sigma, because the term which we have used earlier is the mean free path, is proportional to the mean free path, and this mean free path is inversely proportional to temperature. So, higher the temperature is, lower is the mean free path, greater is the possibility of the collision with the phonon modes of the lattice vibrations. So, ultimately it is the lattice vibrations which are much more important than just the static ion core. So, the temperature dependence now becomes sigma is proportional to 1 by T as per our experimental observations which we have seen earlier. So, this therefore, this so far as this particular aspect is concerned, the temperature dependence, the free electron theory is certainly satisfactory, and one can explain the temperature dependence, that the conductivity will decrease as a function of temperature, or in other words the resistivity will increase as a function of temperature. So, so far this is useful, but it has also its limitations. We will also see what are its limitations. Now, some more phenomenological observations. The temperature increases atomic vibrations leading to increased collision and therefore enhanced resistivity, that we have just seen. However, the dependence is different at different ranges of temperature. We have earlier seen, just the earlier slide, that sigma is proportional to 1 by T, inversely proportional to 1 by T. But this linear proportionality is not always true, and that is what it has been shown here, that both LF and tau, tau is the relaxation time. I think it was introduced earlier, but not discussed that much. Tau is the relaxation time, that is the time elapsed between the two collisions or two consecutive collisions. So, LF is the actually the distance, and tau is the time. So, both LF, the mean free path, and tau are proportional to 1 by T cube when the temperature is very low. So, whereas it is slightly elevated temperature, they are proportional to 1 by T. Okay. So, that is what we have already discussed, that there is a 1 by T dependence of sigma. However, at very low temperatures, again the slope changes. The variation of course remains more or less same, but the actual quantitatively the slope is different. So, it becomes more flatter. Now, in addition to temperature, there is always, I have shown you some experimental curves in which we have seen that addition of impurities like alloying elements also increases the resistance or decreases the conductivity. The resistivity of a metal increases with the addition of impurities or the alloying elements content at all temperatures, irrespective of temperature. This is almost an independent phenomena irrespective of temperature, and this is also very important, particularly when we are dealing with very highly conducting materials like silver, copper, or gold, and so on. So, where conductivity plays a very important role. Many technological applications, whether it is high power applications like overhead cables or underground cables, or even microelectronic circuits where conductors are often used as a charge transport path. The conductivities are of very great importance. So, the alloying elements, whether we should have a alloy, metallic alloy, or a pure metal, that is determined the effect of the effect of the alloying elements, and it has been seen that the resistivity of metal increases with the addition of impurity alloying element content at all temperatures. And these are basically, the explanation is very to a large extent simple, that we have more barriers to the movement of the charged species, that is the electrons here. So, the electrons not only collides with the or interacts with the phonal mode of the lattice vibrations, but also if there is a impurity, it also acts or impedes the motion of the electrons, and that is how they actually retard the movement. So, the conductivity gets decreased. And this combined effect, this is particular, this system or this effect is actually called Matheson rule, where the scattering is by impurities. So, this one is by the scattering by the lattice vibration or the thermal scattering, and this is called the impurity scattering, and that is empirically, actually it is more or less empirically described by the Matheson rule. So, the combined effect is in terms of resistivity now. Resistivity is rho t, which is a function of temperature, and also resistivity is a function of impurity concentration. So, both of them more or less are independent of each other. Okay. The temperature has its own effect, whereas rho has its own effect, and finally, these are, there is a combined effect both of them. And this is the curve which, or this is the plot which we have already presented, and but just for completeness, sake of completeness, once again we are giving you this because it describes many different other points we have discussed so far. For example, this is the resistivity curve of pure copper, where is basically there is no impurity effect, it is primarily the temperature effect. Okay. So, it is the temperature effect which changes this curve, and you can see here we have two different slopes. This is linear, whereas closer to the absolute 0 or as we approach absolute 0, there is a slight change in slope, which we have just mentioned. This is 1 by t cube. Okay. No, this is not the one, sorry. Yeah. So, this is at high temperature, this is 1 by t, and closer to absolute 0 it is 1 by t cube. So, on the same curve both of them have been reflected, and so far as the impurity effect is concerned, it is independent of temperature. At all temperatures there is a impurity effect. So, there is a vertical shift. As soon as you put some other impurity, there is a vertical shift at all temperatures, okay, and it is almost parallel to each other. So, the impurity effect is almost independent of the temperature, and the temperature is also independent of impurity, and it is proportional to the impurity content. So, higher is the impurity content, more and more solute atoms are put in the alloy, more resistance change. So, higher is compared to pure copper, the copper nickel alloy either of 2% or 3% nickel has a increased resistivity or increased resistance. So, this is what they say, the increased phonon scattering. As we increase the temperature, there is increased phonon scattering, and the vertical direction, as you increase the impurity content, there is a more impurity scattering. Okay. So, ultimately both of them actually acts as a impurity scattering. Here it is mentioned as impurity scattering, and one can see this gap or this distance of separation is more or less constant throughout the temperature. So, once again it is independent of temperature. Well, to complete this discussion, so ultimately we find that the obstacles or different kind of scattering centers give rise to resistance of the metals. Temperature has an effect, but the obstacles are like this. Other charge carriers of the same or different type, okay. If it is cations or anions, they can also collide with others. Electrons can collide, of course, they can collide primarily with the phonon mode. Vibrating atom core, the phonons, the crystalline defects, the point defects, line defects and surface defects, these are also add to the increase of resistance of the metals. So, it is not only the crystal structure as such, but the crystalline defect or sometimes dislocations, all of them do contribute to some additional resistance to the system. And if you want a very low resistance material, one must have devoid of all these imperfections, and impurity atoms we have already discussed in details. So, we have discussed two different models, the ideal gas model and free electron theory model. While ideal gas model is not satisfactory to explain the particularly the temperature dependence of electrical conductivity of the metals, free electron theory do give rise to that, but in addition it also has some other importance which will be seen later. But one thing the free electron theory is not satisfied or is not satisfactorily explains, that is the why only metals have so higher conductivity and semiconductors have different kind of conductivity, different kind of temperature variation of resistance or conductance, and why some other materials are insulators. What is the commonality between them? Is there any commonality? Can we have an universal theory? And you have an universal theory which explains the properties of electrical properties of all the materials together, because we have seen the conductivity values or the conductivity levels or resistance levels are widely different from materials to materials, right. Some of them are extremely good insulators, some are extremely good conductors. So, is there any correlation between them? Is there any common factors which actually control these parameters? So, yet both these theories, free electron theory as well as ideal gas theory, is not just sufficient to explain these properties and explain this behavior of the solids as a whole. So, we should then look for some other model or some other theory which can possibly explain many of these properties or many of these behaviors. So, in that context, band theory becomes very handy, and band theory is very important as far as today's knowledge is concerned. So, once again we are talking about the electrons, free electrons, because those are the major charge carriers here. So, the free electron theory can explain many of the properties of metals, but it cannot fully explain why some solids are insulators or semiconductors. Well, for conductors it is okay, but the behavior of the semiconductors and insulators are quite different, and one major difference, in addition to their level of conductivity, the absolute value of resistance or conductance, their temperature dependence are completely opposite to that of metals. So, free electron theory from that point of view cannot explain the temperature dependence of the resistivity of insulators or conductors, so semiconductors. For metals we assume that the electrons are free. However, there is a question mark. We still do not know how free are they in different solids. In metals certainly they are quite free, but in many other solids possibly they are not that free. There is some kind of localization, then kind of attractiveness with the ion cores. So, as such the bonding, chemical bonding is different in metals, insulators as well as semiconductors. The electrons which we assume that they are completely free may not be so. So, the more exhaustive quantum mechanical approach is necessary. A realistic potential for the electrons is required to be considered. So, if we remember that in the free electron theory we have seen or we have considered that the potential is constant. So, the electron is moving in a potential, constant potential, which is fairly low potential or negative potential compared to the end of the solid. So, at the end of the solid there is a very high potential which the electrons are not able to cross over. So, the electrons are confined within the volume of the solids, that is understandable. But is it true that the electron is actually moving in a constant potential across the volume of the material or the length of the material? Possibly not, and that is the basis of the band model. The more exhaustive quantum mechanical approach is necessary. A realistic potential for electrons is required to be considered. So, what is that realistic potential? Well, we have seen earlier or we have considered in the free electron theory that the potential is constant. In fact, in this band model it has been assumed that the potential is really not constant, and which now everybody believes that is more realistic. So, we have some ion cores, these are the positions of the ion cores, lattice sites where the atoms are residing, and these are the potentials, these are the electric potential, variation of the electrical potential of the electrons with respect to its position. So, earlier we have shown that it is a constant potential all through. Now, we are saying it is not a constant potential, it is a variable potential, and particularly just near the ion cores, these are the positions of the ion cores. So, near the position of the ion cores the potential is very low, whereas away from the ion core the potential is high, which means the residence time for the electrons is not uniform throughout the length and breadth of the solid. So, more time it spends near the ion core than away from the ion core. So, that is a more realistic situation, and of course, that makes the mathematics little complex, much complex than what we have seen earlier. So, however, it possibly gives us a more realistic representation of the situation. So, this is what they call a periodic potential, one dimensional. Once again it can be considered one dimensional or three dimensional, and three dimensional solutions are much more difficult. However, people have tried one dimensional problems and tried to solve them and found what is the ultimate effect. So, this is a in one dimension, this is the what we call the periodicity. This is an expression of periodicity. U is a function potential as a function of x, x is this horizontal distance, and so this function is equal to the u x plus d into n. So, at any point at a distance d multiplied by an integer is the number of lattice sites. So, at different, so it is a multiplier, it is a kind of multiplier, and d is the distance between the two consecutive lattice sites, two neighboring lattice sites. So, if that be so, then whatever is the value of u here, it will be exactly the same at there, sorry, at here. Okay. So, it is periodically varying and having coming back to the same value. So, that is the description of how the periodicity of the potential can be described mathematically. Okay. So, d is the distance between the two consecutive or neighboring ion cores. If that is so, so this is a symmetric way, symmetric distribution, but a variable distribution. So, this is the distribution which has been considered. And then of course, it is a much more complex problem. We may not be able to discuss each and everything, and we may not need that also, except that we need what is the ultimate conclusion and what is the outcome of this mathematical analysis. Now, to do the mathematical analysis, there are certain theorems, certain considerations, certain assumptions and so on. So, just try to introduce the names or the particular idea. Each electron in a crystalline solid belongs to each and every atom of the solid, forming an electron cloud. Once again, we have an electron cloud, no doubt, but so electron cloud means, that is the definition of the electron cloud. That means the electrons are actually not specific to any particular lattice sites, although there is some kind of probability function, because we have a periodicity and the near the lattice sites there is the potential is less. So, the probability is more, but it is not static at any particular point. So, it is moving around, but with some some kind of a time sharing basis. More time it is near the positive charges than it is away from the positive charges. So, but the electron cloud still exists, and the electron concept of electron cloud still exists. The probability of finding an electron at any of the atomic sites of the solid is same. That means, irrespective of the particular site, the probability at this site and this site is same. Okay, that is what it also assumes. So, there is a perfectly periodic lattice. So, one can say more or less in the same manner as the potential distribution. Earlier we have seen the potential is ux plus dn. Here it is not the potential, but it is probability. So, probability of finding electron at x is exactly equal to the probability of finding the same electron at x plus d. So, it is moving at a very fast speed, and the probability of finding out that electron at a particular space or a particular site is same. Of course, not everywhere, but on a periodic manner. And this probability is actually nothing but the psi x square, which means the psi is the Schrodinger's function or Schrodinger's equation, Schrodinger's function. So, psi x square is actually the probability. So, that actually psi square, that actually the potential distribution of the how one can express the potential of the electron in the periodic lattice. Well, once again I will not go to the details of that, just 1 or 2 points. This is what we write as the Schrodinger's equation. This is a Hamiltonian of k and psi, and then it gives rise to this value of k h, or the Hamiltonian h bar. Again, once again we are coming back to the similar equation, similar term, that k term, the wave vector term, as well as the Planck's constant, and 2m is the mass, m is the mass or the effective, it is called the effective mass. So, the E again is the kinetic energy, which we have discussed earlier in terms of the free electron theory. K is the momentum vector, okay. And then this is what they call the free electron kinetic energy Hamiltonian. Okay. So, ultimately it becomes this value, and to solve some of these equations we have to take some kind of assumptions, although this may be a more realistic potential variation, but for solving the equations, the complex equations, one is to take make things little simplified, a kind of square well or a rectangular well instead of a varying wave or a continuously varying wave like that, a potential like that. So, the approximate potential variation has been used by the under the Kronig Penny model, and the basic philosophically I am just letting you know that this variation, instead of this variation, one has used a more simpler variation, although it may not be exactly realistic. This may be a more realistic, but it provides us more or less the same outcome. So, using that concept or the assumption, and also at this point one has to consider the so called Bragg diffraction, because the electrons are actually waves here, and so these waves are passing through the lattice. So, as we know that whenever there is a periodic lattice and through which there is a electromagnetic wave is passing through, there will be some scattering, and that scattering sometimes at some under certain conditions it becomes a constructive interference, and that is given by so called Bragg diffraction, that is the n lambda equal to 2 d sin theta. So, that also applies because electron is being considered here as a wave, a kind of electromagnetic wave. So, if that is so, these electrons get scattered and diffracted through a periodic lattice, and the Bragg diffraction actually requires a periodic lattice. Okay. Without a periodic lattice, Bragg diffractions cannot be expected. So, since we have a periodic lattice here, we are talking about a periodic lattice, the potential is varying. So, we also have the possibility of Bragg diffraction of the electrons itself. So, in this case the Bragg diffraction means at certain planes, crystallographic planes, the electrons gets not diffracted, a constructive interference takes place, and it is actually reflected back. So, the electron cannot pass through, electron as if it is observing a mirror plane, and the electron comes back. So, there is that, along with this concept is also important, or it gives rise to this kind of a situation. Therefore, you have some kind of a Bragg diffraction taking place within the lattice, periodic lattice, and that is also impeding the motion of the electrons. So, the motion, the electrons becomes at certain levels, the electron becomes it becomes, the energy barrier becomes so high that the electron cannot go through. So, it comes back and reflected. So, there will be some kind of a forbidden levels or forbidden energy gaps, which we will be discussing maybe in the next class, because this time for this class is over now, and thank you for your attention.